So how to run any quantum program on quantum circuit. This is basically quantum coding, and we are going to use QISKit, which is provided by IBM Quantum Computer. It's an open source platform, so everyone can use. So let's get started. So first you have to create a IBM QX Brains account. Then we similar page like this, and here there are your quantum chips. There are Melbourne SX, London Vivo. These are real quantum chips, and these are quantum simulator. This is a simulator basically. So first there is two sections here. This is circuit composer, which is used to directly create circuits. As you can see, there are the gates provided: Hadamard, phase gate, X poly, XYZ gate, identity, and U1, U2, U3, etc. etc. So this is pretty simple, but the scope is limited. If you want to measure different on different basis, uh, so measure tomography, expectation value, these are this kind of things. So you have to use quantum programming, and this can be done by here. This is QISKit notebook. So let's create a new notebook. Create a bell circuit. First we define it will be. So first we have to create circuit. So this will create a quantum circuit, and we are going to use two qubits. So this is two qubits, and this is two resistor. So first, as you know, the bell circuit, it contains a Hadamard on first qubit and a C naught on first and second. So first we are going to create a Hadamard on first qubit. So to create a Hadamard first qubit, we first define the function. Then for Hadamard, this will create a Hadamard on first qubit. So first qubit represented by 0. So this is 0. Then and C naught get uh, 0 and first qubit. For this we're going to bell dot C naught. This is a control X. So control naught CX is defined as control naught. So 0 will be control circuit, and first qubit will be target circuit. So the will represented by a comma. We represent this by a comma. 0 will represent the first qubit, and 1 the 0 will represent the control qubit, and 1 will represent the target qubit. We're going to measure for measure. We're going to define a function for measure. This is let's keep it like this. Yes, and we're going to the quantums. We're going to measure the quantum circuit defined earlier. This is a 2-qubit quantum circuit, and this will measure measurement will be from 0 to 1 and to 1. Now we're going to print this circuit, or we're going to visualize this circuit uh, to see if we get a exact circuit. So first we're going to write this. First we're going to write the circuit and measurement together. Then we're going to draw this circuit. To run the circuit, we'll use Control Enter. So as you can see, this is a bell state with 2 measurement. Now we are going to run it on a practical quantum circuit. So first we are going to define on which circuit or on which chip or on which simulator we are going to run this circuit. That's so this can be done which backend circuit backend function, sorry. So all these things provided by AER. So do is get backend is run on a quantum simulator. Then we're going to tell this circuit to execute how many times on which packet. So this is execute. We're going to execute this function CIR. So CIR packet. So let's run it for 1000 times. And we're going to print the result. We are going to show how to create a two-state well circuit on IBM QISKit platform. So when you open IBM Quantum Experience and you get two sections, Circuit Composer and QISKit Notebook. So we are going to use QISKit Notebook because it provides basically uh, unlimited types of function, much greater than circuit composer. So we are going to create a two-state bell circuit. So these are the libraries and they will be given previously, so we don't need to worry to import them. So yeah, 2 qubit bell we are going to show how to create a two-state well circuit on IBM Q QSkit platform. So when you open IBM Quantum Experience and you get two sections, Circuit Composer and QISKit Notebook. So we are going to use QISKit Notebook because it provides basically uh, unlimited types of function, much greater than circuit composer. So we are going to create a two-state circuit. So these are the libraries and they will be given previously, so we don't need to worry to import them. So yeah, to qubit state. So first we are going to find the variable is bell. Quantum circuit will create a quantum circuit, and so this is a 2 qubit well set, 2 qubit well state. So we're going to need at least 2 qubits. So 2 comma 2. Uh, this will create a 2 qubit state. Uh, the state require a hardammer on first qubit. For hardammer, you will edge bell dot h on 0, then a C naught controlled by 0, and that targeted on 1. So automatic is C naught is represented by Cx. This is 0, 1. 0 is target, 0 is control, and 1 is target. Now we are going to use measurement. Measurement will be just find a logical mesh. We are going to measure the quantum circuit. So we start measure 0 to 1, 0 to 1. Let's draw the circuit. For this we are going to write the measurement and pair state together. Measurement. Let's so this is the build state with the circuit on the real quantum device. This could be either simulator or real quantum gems provided by IBM. So first we call on which chip or simulator we want to run the circuit. This will be provided by backend. So dot backend. Sorry, we left get because first we want to import the simulator. Let's run it on a simulator. That is Mausam simulator. And which one we want to run?
this circuit. So let's define it again. CIRC plus mains, and now we are going to tell our system to execute it, and the result will store on the result. So we will going to execute, but we will execute first search on which backend. So this is backend, and how many times? As you know, quantum circuits needs to be measured multiple times to get a probabilistic result. So sorts will be, let's say, around 2000 times, and there is there. Now we must visualize it. What are the states we'll get by measuring the bell circuit? So for that, counts equal to result dot. Let's we'll tell our system to get the counts by running quantum circuit name source, and print the counts, and I'll run it. Here is our result. Now let's plot it on a histogram. So plot histogram counts. Now let's run it. Sorry. And as you can see, the probabilities are 0 0 and 1 1 as expected by our expect sorry. So the result which you can see 0 0 and 1 1 state as predicted by theory, and the probabilities are not exactly 50% as there are some errors, noise, etc. So the probability to get 0 0 is 51%, and 1 1 is almost 49%. So this is how I'm going to plot a basic quantum circuit. uh, Create a basic quantum circuit, run it on any device, and get the plot.